Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling inverse trig functions. Let's get stuck into it here, talking about sine of pi over 6. Now this is a little bit of review because we've done this before, but the sine of pi over 6, right, you have to think about the unit circle. This is between 0 and pi over 2, so we know it's in quadrant 1. And we're looking for the y-coordinate of the intercept of the circumference of the unit circle and the terminal side of the pi over 6 angle, which is 1/2. Right, so we're done. Today, though, we're going to focus on a different type of question, though. One where we're given the y-coordinate, or where maybe we're given the x-coordinate of the unit circle, and we have to try to figure out what is the theta measurement that produces that specific coordinate. In this particular example, what I'm saying is what theta measurement gives us 1/2 for the sine function. So this is a question about inverses. So before we get into all the different types of inverse functions that there are, and there's one for each type of trig function, so there's 6 inverse functions we're going to talk about, let's review a little bit about inverses. Okay, so to start off with, inverses undo each other when you compose them. Composition is something that you can do where you plug a function into another function, and inverse functions have this property where when you compose them, you end up getting just x back. You end up getting whatever you plugged into the function. So you can pause the video here. I'm just using this as the example, and then I found the inverse and I'm composing them to show you that you do end up back with just getting x, back when you do this. But inverses undo each other. I like to think about it as the function ties x into a knot, and then the inverse are the directions to untie it, so you get back to where you started. The other thing inverses do is that they have swapped input and output pairs. So if AB is on f of x, then BA is on the inverse, right, of f. And by the way, I kind of skipped over this, but this is how you write an inverse. F inverse of x. That's just a notation. It doesn't mean f raised to the -1 or anything crazy like that. It's just read as the inverse of f, right, or f inverse of x. But anyway, input-output pairs are swapped. So if AB is on f of x, the graph of f of x, then BA is on the graph of f inverse of x. And you can look at this using those same examples that I had just shown you in the previous slide, right? If we use f of x is x cubed minus 1, the inverse of f is this, and I know that because these are exactly flipped. If you read the table this way, those are input-output pairs for f of x, and if you read the table this way, these are input-output pairs for the f inverse of x. What that means is graphically they are reflectionally symmetrical across the line y is equal to x. All of these points, right, on the function f of x, if you reflect them over, those are going to give you the exact points on the graph of f inverse of x. Okay, and that's what this bullet point says. That's kind of a consequence of this one, right? If AB is on f, then BA is on f inverse, means that the graphs are reflectionally symmetrical. It also means that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Pictorially, right, if you use a mapping diagram, typically the picture that you look at for functions is you have an input, it lives in the domain, this is the domain, right, of f, and you run it through the function f, and you land somewhere in the range of f. Well, you can go backwards, right? You can take things from the range of f and map them to the domain of f, and you can do that by using an inverse function. The last thing that I want to say is that in order for f inverse to exist as a function, f of x has to be what we call 1-to-1. 1-to-1ness has a definition. The stipulated definition is if a and b are elements of the domain of f, where a is not equal to b, meaning they're not the same input, then f of a is not equal to f of b, meaning their output has to be different. So essentially, I translated this into being different inputs go to different outputs. You can't have two different numbers go to the same thing, basically. Another translation is that f of x passes what we call the horizontal line test, which is just a way to really quickly see if a function is going to have an inverse that's also a function. Just see if a horizontal line, right, intersects the graph more than one time. If it does, it's not 1-to-1. So x squared, for example, is not a 1-to-1 function, because two different inputs, like -2 and +2, give you the same output, which is 4. So back to this question, right? What gives us 1/2 for the sine function? What theta measurement gives us 1/2 for the sine function? Well, to answer this, we could just look at quadrant 1 of the unit circle and figure out what gives you 1/2 as the y coordinate, and it turns out it's this thing. And also all of these things. Yeah. See, there's a problem with the sine function. Given what we just reviewed about inverse functions, your original function has to be 1-to-1 for the inverse to also exist as a function. Now, don't get me wrong, everything has an inverse, right? But not everything has an inverse that's a function, and this is clearly not a function. To fix this issue, what we can do is truncate the sine wave. We can only look at specific portions of it, and then we can say, okay, well, this particular part of the sine wave has an inverse, and we can define it that way. If we truncate the sine wave from negative pi over 2 to positive pi over 2, we do get something that passes the horizontal line test. So this is the sine wave where x is only an element of negative pi over 2 to pi over 2. All right? That thing, and by the way, that's in quadrant 4 and quadrant 1 of the unit circle respectively. That can be flipped over the line y is equal to x, and it does give you a function. And this is how we're going to define it. So this is sine inverse of x, or arc sine, which is another name for the same function, is the angle measurement theta between pi over 2 and pi over 2, between negative pi over 2 and pi over 2, such that the sine of theta is equal to x. So the domain of arc sine is negative 1-to-1. Since that was the range of the sine wave, it's now the domain of the inverse function. And then since we truncated at negative pi over 2 to pi over 2, the sine wave, that was our domain of sine, now it's the range of arc sine, because inverse functions have flipped input and outputs. Okay? Also, all this inverse stuff exists. So we were talking about function composition. Sine of x ties x into a knot. Well, and sine inverse undoes that. So you're just going to get back to x. Now, this is only true for when you're looking at inputs between negative pi over 2 and pi over 2, since we had to restrict the domain of the sine function to just being negative pi over 2 to pi over 2. It only works in that case. Similarly, the other direction of the composition, right, if you're starting with the sine inverse of x, you can only plug in things that are between negative 1 and 1 for sine to be able to undo them. Now, this helps explain why we're defining the arc sine function as a theta measurement such that the sine of theta is equal to x, because it's a little backwards, right? The definition, this is the definition really for sine inverse of x, but we're defining it to be sine theta equals x. Well, it's because if we have this equation, sine of theta is equal to x, and then we use the inverse property, right, the beginning, right, of the inverse stuff box, we'll just take the sine inverse of both sides. Doing that is going to eliminate the left-hand side because the sine inverse of the sine of theta should just give us back theta. Since we're working in this domain, that's just theta, so theta is equal to sine inverse of x, which is exactly how we defined it. So here's some examples of evaluating the sine function. If you're an absolute baller, you can pause the screen here and you can just go through this and look at the unit circle, figure out which angle measures produce these specific values for sine, but I'm going to go through them one at a time here anyway. We already did the first one, right? Sine inverse of 1/2 is pi over 6. It's really because the sine of pi over 6 is a half. The input of our function is the answer to the sine of the answer to the sine inverse of our input. Boy, that's not confusing at all. But that's how inverses work, right? The other thing you can do is you can just look at, well, here's the graph of sine inverse. If you plug in 1/2, you get pi over 6, right, as the output. Sine inverse of negative square root 3 over 2 is asking us which angle measure produces negative square root 3 over 2 in quadrant 4 or 1, right? Because it's got to be between negative pi over 2 and pi over 2. Well, since it's negative, we're definitely in quadrant 4, some kind of negative angle. The only angle that produces negative square root 3 over 2 as a y coordinate is negative pi over 3. So the sine inverse of negative square root 3 over 2 is negative pi over 3 because the sine of negative pi over 3 is negative square root 3 over 2. Arc sine is the same thing as sine inverse, so we're finding the sine inverse of square root 2 over 2. What theta measurement produces square root 2 over 2 as a y coordinate on the unit circle? Well, it's got to be in quadrant 1 in this case, and it's pi over 4, because the sine of pi over 4 is square root 2 over 2. This one's a little bit more interesting. It's a sine inside of a sine inverse function. So we have the sine of pi over 3. Okay, the sine of pi over 3, we know how to do that. That's square root 3 over 2. Just looking at the unit circle, it's the y coordinate when the terminal side of pi over 3 intersects the outside of the circle of the unit circle. Now we're finding the sine inverse of square root 3 over 2, so we have to revert back to these types of questions. What angle measurement produces square root 3 over 2 as a y coordinate on the unit circle? But we've kind of already answered that. It's pi over 3. Right, in fact, in this particular case, what we're doing is we're just running pi over 3 through the inverse stuff. X is pi over 3, so the sine inverse of the sine of x is just going to be x. So the sine inverse of the sine of pi over 3 is just pi over 3, really by definition of inverses. Now, when we get to this one, you might think, okay, now we can just do the same thing that we just did for the previous one, right? We have the arc sine of the sine of 5 pi over 4. So let's just use the inverse stuff just like we did for the last one, and so our answer is going to be 5 pi over 4. No. You see, 5 pi over 4 is not inside of the interval negative pi over 2 to pi over 2. The arc sine can't give you 5 pi over 4 as an output, right? Its range is specifically between negative pi over 2 and pi over 2. So it's in quadrants 4 and 1 respectively. So what we'd have to do then is just take this in steps. We can certainly do the sine of 5 pi over 4, right? That's something that we can do. It's negative square root 2 over 2, right? It's definitely square root 2 over 2 because the reference angle is pi over 4, something that we already did over here, but it's negative. And since it's 5 pi over 4, we know that's bigger than pi, so it's got to be in quadrant 3. Okay, and then at this point, now we're changing the question to like what we've been doing up here. What is the arc sine of negative square root 2 over 2? What angle measurement between negative pi over 2 and pi over 2 gives you back negative square root 2 over 2 for the y coordinate on the unit circle? And that's negative pi over 4. Okay, so in this case, we get the arc sine of 5 pi over 4 is not just the input, right? You don't just get back 5 pi over 4. So you do have to be a little bit careful when you're doing these things. Make sure that the only time you can say that it's equal to the input, right, is if that input is between negative pi over 2 and pi over 2. If it's in quadrant 4 or quadrant 1, respectively. 5 pi over 4 is not, so we have to take it in steps. Okay? So now let's move on to the cosine inverse function. Okay, here's cosine's wave. Similar problem, does not pass the horizontal line test. So we're going to have to truncate the cosine wave. This time, though, we can't go from negative pi over 2 to pi over 2 because that would give us this piece of the graph here, which still doesn't pass the horizontal line test. So instead, we break it up between 0 and pi, which is nicely quadrants 1 and 2 of the unit circle. That can then get reflected over the line y is equal to x, and that produces the graph for the cosine inverse, or the arc cosine function. Interestingly, you do not get any negative outputs for the cosine inverse function, which is kind of cool actually. But it's still the same definition as sine inverse, it's just in a different range. Domain, rather. Now it depends on which one you're talking about. I'll just read this. The arc cosine is the angle measure theta between 0 and pi such that the cosine of theta is equal to x. The domain of arc cosine is negative 1 to 1. The range of arc cosine is 0 to pi. So again, we get no negative outputs. And then, of course, all this inverse stuff is still valid, but only between 0 and pi for when you're taking the cosine inverse of cosine of x. That's going to give you x only in these cases. And the cosine of the cosine of inverse of x is going to give you x, but only if you're plugging in things negative 1 to 1. Tangent, right? Moving right along to tangent. Tangent's just a repeated graph over and over for every period. Its period is pi. Let's just take one of them and reflect that thing over the line y is equal to x, and here we go. Here's tangent inverse, or arc tangent. It's the measure of angle theta between negative pi over 2 and pi over 2 such that tangent theta is equal to x, and its domain is all real numbers. You can plug whatever you want into the tangent function. However, its range is very limited. You have negative pi over 2 to pi over 2. There's horizontal asymptotes, right, for the for tangent, well, also true for cotangent inverse, which we'll get to in a second. But tangent inverse has horizontal asymptotes because its original function, right, the inverse of tangent inverse, which is the tangent function, has vertical asymptotes. But when you reflect a vertical line over a diagonal, like y is equal to x, you get a horizontal line. So the vertical asymptotes of tangent actually become horizontal asymptotes for tangent inverse. All right, here's the other three. Cotangent, cosecant, and secant are all going to be limited by 0 to pi, negative pi over 2 to pi over 2, and 0 to pi respectively. The cosecant and secant functions are very interesting because you're breaking them up not in one of its kind of parabola looking shapes here. We break it up kind of halfway, and that gets us all the possible outputs for cosecant and secant. But you flip those over the line y is equal to x, and you get all of this stuff here. So I invite you to pause the video. All of them have horizontal asymptotes. Cotangent inverse has 2 of them at 0 and pi. Cosecant has one at 0, and secant has one at pi over 2. And of course, I mean the inverse, right, of all those functions. But the domains and ranges of all of them are given here, so if you want to put these in your notes, feel free to do so. I always find myself pretty much exclusively using tangent inverse, cosine inverse, and sine inverse. All the other ones are kind of niche, and you could theoretically get around using them, but there are times where that could be useful to use them. So we've just done a bunch of this setting up all these inverse functions, but what can we do with it? Right? What can we do with these functions? Well, for starters, we can solve for angle measures, right? This particular picture relates an angle measure theta with its opposite side and its hypotenuse. The ratio that relates all those things is sine. So we could say the sine of theta is equal to 10 over 13. To solve for theta, you just take the sine inverse of both sides of the function, right? Whatever you do to one side, as long as you do it to the other, you're keeping the equation balanced. The sine inverse of the sine of theta is just theta. So now we just need to calculate the sine inverse of 10 over 13, which you could run through your calculator. Mine happened to be in degrees, so I solved for theta in terms of degrees, so I got 50.28 degrees. But this is kind of the main application. We can solve trig equations. We can solve trig functions now for the angle measure. So we can do stuff like this, right? Solve 8 sine squared theta plus 7 is equal to 9, specifically where theta is between negative pi over 2 and pi over 2. Right? I mean, you could treat this almost exactly the same as 8x squared plus 7 is equal to 9. So we're going to start off by moving the 7, right? Get the sine squared piece by itself. After this, we'll divide by 8. So we get sine squared theta is equal to 1/4. And by the way, I should mention, sine squared theta is the same thing as sine of theta quantity squared. So now I'm going to square root both sides. Right? That's going to give me plus or minus 1/2. You get plus or minus the square root of 1, which is 1, divided by the plus or minus the square root of 4, which is 2. So this breaks up into two different equations. Sine theta is equal to positive 1/2, or sine theta is equal to negative 1/2. Solve both of them by taking the sine inverse of both sides, and you get pi over 6 and negative pi over 6. Now you might be wondering, well, what if this part didn't exist? Well, then you just add some stuff to it, but we're going to get to that in a later video. You can also do really cool things like this. Find the tangent of cosine inverse of x. Okay, it seems kind of weird, but we can do something like this. First, we're going to let theta be equal to the cosine inverse of x so that we can set up a triangle where the cosine of theta is equal to x over 1. So theta is the angle measure that I drew here. Its adjacent side is x. Its hypotenuse is 1. That's this ratio, kind of exemplified in a triangle. We just need to know what the tangent of theta is, right? Because if this whole thing is just theta, right? This whole thing is theta. This is just really the tangent of theta that we're looking at here. So we just need to come up with this side length. Okay, well, that's just Pythagorean theorem stuff. So eventually we get the square root of 1 minus x squared. So the tangent function is opposite over adjacent. So we get the square root of 1 minus x squared. It's all divided by x. Pretty cool. All right, so I think this video has been long enough. We're going to stop it here. Hopefully this was helpful. Hopefully you learned something. Thanks a ton for watching, and I'll see you in the next one. Bonus knowledge! Now, you might have been wondering throughout the video, does the tangent inverse of x equal the sine inverse of x divided by the cosine inverse of x? I mean, we know the tangent function is sine over cosine, right? But does that hold true for inverse stuff? Well, let's just plug in a value to see if it holds true. Well, if you plug 1 into the tangent inverse function, what you're asking is what angle measure produces a value of 1 for tangent that's between negative pi over 2 and pi over 2, And the only place that does that is pi over 4. So tangent inverse of 1 is pi over 4. Okay, so one side of the equation is pi over 4. Now, if we don't get pi over 4 here, we'll have our answer. So when you plug in 1 to sine inverse and cosine inverse, let's do sine inverse first, you're asking what angle measure produces a value of 1, that's between negative pi over 2 and pi over 2 for sine inverse, on the unit circle, right? It's got to be a y coordinate. Well, pi over 2 does that. Okay, that's not pi over 4, but that's fine. We're going to divide this by something. So let's look at the cosine inverse. Okay, cosine inverse of 1, also asking what angle measure on the unit circle produces a cosine value of 1. And it is 0, which is not good because you can't divide by 0. So, okay, no, tangent inverse of x is not equal to sine inverse of x divided by cosine inverse of x. And we just proved it via a counter example. All right, so hopefully you guys learned something. Thanks a ton for watching, and I'll see you in the next one.